S be a subspace of Rn with basis v1 through vk, and I'm giving it a name. I'm calling that basis B. For every vector u in S, there is exactly one way to write u as a linear combination of the vectors in that basis. I'm not going to go ahead and prove this theorem, but you can look in the book for that. However, this theorem motivates the following definition. We call the coefficients c1 through ck the coordinates of the vector u with respect to B, and write this brackets around the u with a subscript b equals this vector. Let's look at a couple examples. Let S be the span of the vectors 1, 2, 3, 4, 5, 6. Then, since v1 and v2 are not parallel, they're linearly independent, and therefore the set B equals v1, v2 is a basis for S. Now let's look at the vector u equal to 6, 9, 12. Then one can show that u is 2 times v1 plus 1 times v2, and therefore, using the definition of coordinates, the coordinates of u with respect to B is the vector 2, 1. In particular, notice that while V is a vector in R3, it only has 2 coordinates with respect to the basis B. Let B be the standard basis of R3, and let u be the vector 6, 9, 12. What are the coordinates of u with respect to B? I'll give you a moment to try and figure that out. Now that you're back, let's see. Well, we know that u is equal to 6 times e1 plus 9 times e2 plus 12 times e3. Therefore, using the definition of coordinates, the coordinates of u with respect to the basis B are 6, 9, 12. Oh, that's just the same thing as what we started with. That's interesting, and that's not an accident.